This is Gandhi, and I want to talk to you about QGIS expressions. This is a version of the talk I gave at the QGIS International User Conference 2024 in Slovakia, and I wanted to share it here with all of you. Expressions are one of my favorite parts of QGIS. I've used expressions a lot, primarily for analysis, and some of you may have seen my tutorials and course materials on that. But today I want to talk to you about using QGIS expressions for visualization and doing some things which are unexpected but fun. And maybe you'll discover some hidden parts of the expression engine that you were not aware of. We'll start with the basics of expressions and understand what expressions are, how they're used, and how can you use them within the QGIS environment. Then I want to cover 3 specific use cases. We'll see how to take a problem and then solve it step by step using expressions. All of this are solved using a single expressions, but we'll do it step by step and see how we can build that expressions. There are a lot of links in the presentation. If you want to get access to the presentation, you can scan this QR code or note down the bit.ly link. So let's get started. What is an expression? Well, expression is a piece of code that contains some functions, some operators, and when you evaluate this, it results in a value. In the context of QGIS, you can have an expression which consists of some built-in functions, some operators. You can refer to the features and the attribute values in geometry, and then the QGIS expression engine evaluates this and gives you the output of each expression for each feature. Many people ask, what is the language of this QGIS expressions? The closest equivalent I think about this is like an Excel formula. So if you're used to writing formulas in a spreadsheet, the expression feels very similar to that. But the expressions are a language in itself, and once you learn it, you'll be able to use this within the QGIS environment. The QGIS expressions follow a certain set of rules. Let's learn about them. If you write an expression with something in single quotes, that will be interpreted as a text. So if you just say in quotes name, that value will be just the string name. So that's simple enough. But if you put double quotes around any piece of text, that will be interpreted as referring to the field of that name, and that value will be replaced by the value of that attribute. So in double quotes, name will take the current features value of the attribute name and replace it with that. So in many programming languages, single and double quotes are equivalent. In QGIS expression engine, they have very different meanings. You can also have variables which start with an @ symbol. So when you refer to a variable, the variable often has values which change depending on the context. The values all can refer to the current feature. You can have also variables that are project or layer specific. And finally, when you have something in parentheses, that's the syntax for calling a function. QGIS comes with its own library of built-in functions, and if you refer to any of those functions, you need to use the parentheses. Some users of QGIS will also remember that there used to be, and there still are, some functions that start with the $ syntax. As of the newer versions of QGIS, they have been deprecated, so there are equivalents with the @ symbol that you should use, but again, they'll be around in QGIS for a long time for backwards compatibility. So these are the kind of 4 main rules you need to remember when you are writing an expression: single quote for strings, double quote to refer to the field, @ to refer to a variable, and then parentheses to refer to a function. Let's take a simple expression like this. In this expression, we are saying length of geometry greater than 100. Now here, the length is a function. Remember, we are calling a function with a parenthesis and say, take the value of the geometry variable, which refers to the geometry of the current feature, which the expression is being evaluated. So the length function will compute the length of that, and then we have an operator, which is the greater than. We'll compare that against a value. So there are 4 pieces to this expression, and once the expression engine takes this, it'll evaluate it and it'll result in a value such as true or false. And this is your result. The great thing about expression is that you can write expressions and which contain other expressions. So they can be nested, and this gives the expression engine its true power. Let's say here we want to compute the azimuth of a line. So we have a function called start point. So this is a function that takes a geometry and gives you the start point. So let's say we have line geometry, and this function will give you the start point. We also have a similar function called endpoint, and we'll give you the endpoint of the line. So let's say you have a line with 2 points, start and end, and you run this function, you get both the start and end point, and then you call the function azimuth with the start and end point, and you'll get the azimuth value. If you read the documentation for azimuth, this says the written value will be in radians. So here we already used a function and then took the result of the function and used another function. We can keep going. We can say, I want the results to be in degrees. We can call the function degrees and then pass on the whole expression, the previous expression, as the input to this, and you'll get the answer. So here now we nested 3 functions, and this was a single expression, but we could do something very complex where we compute the azimuth of a line in degrees. Every piece of QGIS uses expressions in some form. Most people, when they start using QGIS, the first encounter for them with the expression engine would be when they are trying to add a new field or update a field value. You can use an expression and that computes a new field value. You can also change the geometry of features. We're going to learn about geometry generators, a really powerful feature where you can render the geometries by applying an expression. You can also create new geometries using an expression. When you're working with symbology, the expression engine is everywhere. Wherever you see this button called data defined override, you can override the value of that parameter for the symbology or labeling or placement of your layout, etc., with an expression, and then you can make that dynamic. So if the expression changes, your value will update. You can also use it all throughout the processing framework, whether you are trying to run a processing tool. Many tools have a way to add expression as part of that. You can also use them in batch processing and modeler to dynamically compute values. And again, they are everywhere. I think every piece of QGIS has a way to control that aspect with expressions. So let's see some examples and see what are the cool things we can do with expressions. The first example I want to show you is the example of creating a cartogram. Cartogram is a type of map visualization where you distort the shape of the feature to refer to a particular variable. I particularly don't like the traditional cartograms because they often are very hard to interpret, but I like this kind of version of cartograms, which are called the non-contiguous area cartograms, where you take a feature and you scale it down to in proportion to a variable. So let's say you want to display population density as a variable. You can change the area of each feature in proportion to its area density. And now you can create a population cartogram like this, where it shows how, if all the states of the US had the same population density, how would it appear? And this is a much nicer visualization. You can see all the empty spaces are quite informative. You can see where there are more empty spaces, it's less dense area. So the eastern part of the US is much more densely populated and western half. Also, when you're creating this cartogram, it'll be nice to kind of show the progression of the shapes from the original shapes to the target shape. And this shows what was the original map and then how we are scaling those features. So we want to see if we can create an animated cartogram in QGIS that takes your original data and scale it. The whole animation, the whole scaling is just a single expression. But we're going to do it step by step and understand how we can write an expression to create an animated cartogram like this. We'll start with some data. Here's a vector layer of the United States states. We have 2 attributes here. We have the name of the state and we have a column called population estimate 2023. This is the population of each state. First step we want to do is we want to compute the density of each state. So to compute population density, we need to divide the population by its area. So we can have an expression like this where we can say double quotes pop estimate 2023, which is referring to the value of that field pop estimate 2023 divided by the area of the at geometry. So at geometry is the geometry of the current feature, and the area function will give you the area. Again, many of you might be used to writing this as $area. So again, this is the newer and more preferred syntax now. So we get value of density for each of those states, and now we can use this values to scale our features. We can choose the feature with the highest population density. In this case, you can see the New Jersey has a very high population density. What we want to do is we want to scale all other features so that its density is proportion to the density of New Jersey. So if the density was half, then the feature size will become half of the original. So we want to compute the proportional density by comparing the density of the current feature and dividing by the maximum of the density column. So this is the expression that will give you that proportional value for each feature. But when we're scaling this, we can't use this value directly. As an example, let's say we have this polygon of area 1 with both the sides being length 1. We want to scale it to half its area. So let's say we want to take the area and scale it to half its area. what would be the length of that polygon, length and breadth of this polygon? It won't be 0.5, right? If you do 0.5, the area wouldn't be much lesser. So if you want to get to half the area, each side has to be square root of 0.5, and that is 0.707. So now if you want to scale something by half, you need to apply the scaling factor of square root of that factor. So we can do the same here. We want to scale each feature in proportion to its density, or whatever variable you are trying to map. We want to apply the scaling factor, which is the square root of that factor. So we can now use the sqrt function and say whatever scaling proportional density we computed, the scale factor would be the square root of that. And now you can see the scale factor is 1 for the feature having the highest value, which is New Jersey, and then all other features have a smaller scale factor. So they'll be scaled proportionately by that factor. We have a function in the QGIS expression engine called scale, which takes these parameters. You say, give a geometry, X and Y scaling factor, and the center point in which the geometry will be scaled through. So we can construct an expression like this, where we say, take the geometry of the current feature, take the scale factor values, which we just computed, and scale it at the centroid. So keep the center point as anchor and then scale it accordingly. We can apply this in QGIS. We can, instead of creating a new layer with the scale values, we can just apply an expression using the symbology called geometry generator. This allows you to enter an expression which will then create new geometry for each feature, and QGIS will render those on the map without creating a new layer. This is a great way to see the output of your results without creating a new layer and managing new data set. This also helps us that we can dynamically change the expression and see the result here without having to recreate the layer. So once we enter the expression, you will see now we have all the states scaled in proportion to their density, and that looks pretty good. But again, this map is not perfect. We'll update this expression slightly to make it a little better. One of the problems is if you look at the states which are having irregular geometries, the centroid may often not be the representative point. Sometimes it may even fall outside the boundary of the polygon. And so instead of doing this, we can replace our centroid with a better representative point for which to anchor each feature by. And that is something called pole of inaccessibility. This is one of those lesser known hidden functions in QGIS that you may not have come across, but I really like it. I've used it multiple times where I want a representative point to label a feature or to anchor that feature. And this is a function where you can just give a geometry and it'll give you something that's guaranteed to be inside of the polygon, and it's the farthermost point away from the edges. So we can say, give me the pole of inaccessibility of a geometry, and you'll return that point. So now we can take our original expression and replace it with the pole of inaccessibility as the anchor point, and you can see this looks already much better. So now we have updated expression. We still have one more problem. If you look at features which are multi-polygons, so features like islands, this is the island of Hawaii, which has got 8 separate island features. All of the polygons are multi-polygons. They're part of the same feature. So now when you're scaling this, the anchor point, you just use whatever, either the pole of inaccessibility or centroid. It'll be the centroid of the whole feature, which is not ideal. We really want all the features to be scaled independently, and even though it's a multi-polygon feature. So what do? We come to one of my other favorite functions in the expression engine, which allows you to write for loops within the expression engine. So you can now do multiple computation within the expression using this function. The syntax for this goes like this. You give a list of values. So here we're giving a list of values 1, 2, 3, 4, 5, and then you give an expression of what to do with each item. You can refer to each item of the list as @element and then do something. So this expression array for each 1, 2, 3, 4, 5 element plus 1 will evaluate to be 2, 3, 4, 5, 6. So now we can run a single expression for each item in a list. We can do this with our problem where we can say, I have a multi-part geometry. For each part of the geometry, I want to do the scaling. So we use array for each, and we say from 1 to how many parts are there. So in this case, 1 to 8. So for 8 times for each part, you can apply the scaling. So now we can replace this with this expression where we are saying for each part, so we'd say for each part, scale that part. So you have this function called geometry n, which will get you the nth part of the geometry. And for that part, you apply the scaling factor. Once you're done, you'll get a list of geometries. And since we have to put this in our layer, which is a multi-polygon layer, we can run this function called collect geometries, which will convert this list of geometry into a multi-part geometry. So you can see now our features which were not scaling properly now also scale well for the multi-polygon features. So done, we now have a static cartogram which you constructed and it looks pretty good, but we want to do this animation. We don't want this expression to be a static expression. We want to just say, I want to see the progression from the scale factor 1 all the way till the target scale factor, so we know how the features were and how they are now. QGIS comes with an animation framework. We can use the temporal controller to visualize the data through time. Here what we want to do is we say whatever time period we select, at the beginning of our time frame, we want the feature to be at the full size. As it progresses, we want to slowly scale it down till it reaches the target size. So in this case of Alaska, this is the actual size. And as we want the final map to have a size like this, which is again very small because Alaska has very low population density, it will be scaled down to a very small feature. But we want to show this progression from the full feature to the target size. How do we set this up? Whenever you are trying to scale some values from one to the other and you want to do this progressively, you can use this function called scale linear, which allows you to take a value and compute the scale value given target range. So let's say we have a value like 500 and we want to scale it between 0 to 1. So you can say, take the input range 0 to 1000, the input value is 500, compute what would 500 be if the 0 to 1000 was 0 to 1. And again, output of this would be 0.5. So given a target range, we can take each value and compute the value as it falls within the target range based on the input given range. We can now apply this to our feature. For this, we want to scale the features based on the time that this passed. So we have some variables in our expression engine that allow you to control and get access to the current time of the animation. We have this variable animation start time and animation end time, which tell you what is the start and end time of the animation. So this is our target range. So we want to say at the beginning of the animation, we want the scale factor 1. At the end, we want the scale factor to be whatever the target scale factor is. And as we progress, each time frame, each time step is saved in this variable called map start time. So as the time is moving forward, we say we are now halfway through. And that is your map start time will refer to that time at the halfway mark. And then we can use this to say, now we are halfway between this animation start and animation end. What would be the scale factor from 1 to whatever the target scale factor was? So now we can update our expression saying, don't just give me the static output of the scale factor, just the scale factor based on the current time step in the animation. So we can now take the map start time and scale it from 1 to whatever the target scale factor. And now we can see once we update this and as we play the animation, the feature slowly scales from the original size to the target size. And this gives a pretty compelling visualization of how the different states have different population density. And this is the final animation that we could construct. And this again is done using a single expression, but we did it step by step by slowly building out the expression. These are some of the functions that were used in creating this final result. We have step-by-step instructions written on our QGIS tutorial site. If you're curious and you want to try this yourself, do refer to this link and you'll find the step-by-step instructions. Some of the expression I showed on the presentation was simplified a bit to make it easy to understand the full expressions that are given in the guide if you want to do the step-by-step tutorial yourself. Let me show you one more example of using expressions, but for creating a new visualization. So what we want to do is we want to take a layer of contours, standard line contours, and turn this into a 3D visualization that looks like this. We will learn how we can use expressions to dynamically change the geometry and create a new version of that contour geometry so that it looks like 3D. This workflow comes from Stephen Kim. We collaborated on quite a few expression tutorials. You can check out the whole series on our QGIS tutorials website. If you do not follow Stephen Kim, do follow him. He is a genius and he's an amazing repository of expression examples that are always fascinating. So here we start with the standard contour layer. Here in our contour layer, we have this column called contour elevation, which contains the elevation value of each contour. We want to now change the geometry of each line so that we take each coordinate, each vertex of the line, and shift it in the y direction. You can use this function called translate, which takes a geometry and applies a transformation to a target value in the x and y direction. So if we have a point 0, 0, and we can say translate that point to 1, 1, you'll get a point at 1, 1. So it'll just change the point to be at the new coordinates. We can now take this and say we want to translate our each line geometry. In x direction, we want 0 translation. So you should say wherever in the x direction. But in the y direction, we want the shift to be proportional to its elevation. If the line elevation is higher, it should be translated more. If it's lower, it should be translated less. How do we do this? So whenever we encounter a problem like this, where we want to do something in proportion to another variable, we can use the scale linear function that we had just used before. So we take this and say, take the values from our contour elevation column, scale it from 0 degrees y shift to 0.2 degrees y shift in proportion to the range of values that are contained in the contour elevation column. And if your current contour elevation is 500 and the maximum is 1000, you'll get a shift of 0.1. So again, this will be to do a proportional computation using some target value. So we write an expression like this, where we say, take the geometry and scale it based on the contour values. Again, we use the geometry generators here. We come to the symbology. You can see this is what the layer looks like. The expression for geometry generator is add geometry. So just keep the same geometry as usual. But if you replace it with the expression we just built, you'll see that now the layer changes and we see this really nice 3D visualization. And again, this was done using this particular expression. This looks nice, but it'll be nice to apply some color to it. We can go and apply a color ramp from the graduated symbology here. But let's do this using expression to see how we can even update colors using expressions. There are many color related functions in QGIS expressions. One is called a ramp color, where you give it a name of a color ramp and say from 0 to 1, which value you want. So the start of the ramp is 0. End of the ramp is 1, what color you want. So let's say we have this ramp red, yellow, green. If you say give me 0, give me the first color, you'll get the red color. If you say give me the middle color, which will be yellow in this case, and if you say give me the last color of the ramp, which is 1. And again, if you give any value between 0 to 1, it'll give you the linearly interpolated color from that color ramp. We can use some color here. We're using a color ramp called Wiki 1.02. We say apply a color ramp from this based on the elevation value. If the elevation is low, use the color at the beginning. If the elevation is high, use the color at the end. Where do we apply this? Well, you have the color for each line. You can see the color is set to be this pink color, but we can now use this data defined override. Wherever you see this button, we can enter an expression, and instead of that static color, QGIS will evaluate this expression and set the color to whatever the color comes out of the expression for each feature. So we can now enter the expression, and QGIS will say for each line, I'll compute a dynamic color from the ramp based on its elevation and apply it here. And you can see we have now got this different colors for each line. This looks okay, but you can see our ramp goes from like blue to green. And if we do linear interpolation, we have a lot more blue than we want. We want blues only for a very small portion of our initial low elevations. We want the more range for the green. So instead of doing a linear scaling, we have other functions like scale polynomial or scale exponential. We can use different kind of scaling methods. So we can replace our linear scaling function with a polynomial scaling function, and we'll get a result that looks something like this. So this looks slightly better, where we could control how the input range values get transformed to the output range. Again, these are some of the new functions that you may use in your work, especially if you're doing some symbology. The expressions allow you to have much more finer control than doing it through the styling panel. The last example is a short, but something that is quite unexpected use of the QGIS expressions. I saw this a while back on Keith Jenkins's Twitter feed, and I said, wow, this is cool. And at some point I'll try to replicate this. And finally I had the time. I could figure out how to do this with expressions. And you can make maps where as you're moving around your cursor in QGIS, you can make things happen. And this is really cool. We're going to see how to do this using this example of rotating the QGIS icon to always follow you around. We start with the grid, which just create a grid of points using the create grid algorithm in the processing toolbox, and then set the icon for its symbol as any SVG marker. Here we're using the QGIS icon as our marker. So we have this QGIS icons rendered as SVG markers on the point. We want to rotate this QGIS QGIS icons as we follow our cursor around. So we want the tip of the QGIS icon to always follow our cursor position. So let's say if my cursor position is here, we can compute the azimuth of the cursor position and say how much should we rotate the QGIS icon based on the azimuth. If my azimuth is 135, which is exactly the layout of the QGIS icon, that's the current icon rotation 0. So at 0 rotation, we want the azimuth to be 135. If we move our cursor, and let's say our azimuth becomes 225, we want to rotate the icon, which is 225 minus 135, which was the original angle of that point in the QGIS. And now we rotate it by 90 degrees and we make it follow the cursor position. We can keep going. If our cursor position moves here, we compute the azimuth and then subtract 135, which will give us the position that we should rotate our QGIS icon to point it to the current cursor position. How do we do this? Well, we have the azimuth function that takes 2 points and computes the azimuth. We can take the current geometry of the point where we have rendered the QGIS icon and then take this value of the variable called canvas cursor point. This gives you the last position of the cursor. And this is what kind of makes this whole interactive, where as you move the mouse, the variable updates with the value of the cursor position, and you can use that in your expressions. So we can construct an expression like this, where you say, give me the azimuth from the point of that feature to the canvas cursor point, and we want to compute the rotation, which is 135 degrees less than the current azimuth. Where do we put this? Well, there's a rotation parameter for each marker symbol, and we can say don't use a static rotation, compute the rotation based on this expression, and this expression will give you new values as we move around the cursor. So again, the rotation will be dynamic. If you do this and try this out, it doesn't work quite well because the canvas doesn't refresh when you move your cursor. It would be pretty bad for QGIS to have a way where you just move your cursor and stuff gets updated. So the canvas only updates when either you zoom, pan, or do something in your canvas. There's a setting in your layer setting where you can go and say, for this particular layer, I want you to update this layer at a regular interval, even if nothing has happened. And this is what we need to change. If we say change the interval seconds to be very small amount, the layer will update every 1/10 of a second. And now when you move around the cursor, the layer will update every 1/10 of a second, will compute the new azimuth, and will compute the new rotation for the icon. So now when you move around in QGIS, you'll see those QGIS icons are falling around. It's a really fun way to see how you can use expressions and data-defined overrides to do something interesting. Again, you can use it in so many contexts. You can take the position and make the values larger or smaller, can have a zoom effect, or maybe change the symbology of the feature which are near your cursor and so on. Again, the sky is the limit of what you can do with this. I encourage you to try out this when you get time. It's a really fun 10-minute exercise, but again, really nice to see this interactivity in your QGIS canvas. In summary, I wanted to inspire you to give the expression engine a closer look and use it for your next project. They offer very powerful functionality. And for many use cases, you can write some custom Python code and do your analysis or visualization, but you can instead do a single expression, which is much simpler to write. It is much easier for analysts and non-programmers to build and maintain. So it just has a longer life and it can do things much more dynamically. I've been fascinated by expressions for a long time and have written tons of tutorials and courses that leverage those. If you're curious, you can check out tutorials with this, got some visualization tutorials on how to use expressions. We have a whole course module where we teach some advanced expressions in detail. So you can check out those videos. We also have many other use cases documented on our blog where you can see how you can apply expressions for some analytical task. Thank you.